Okay, we'll now talk about section 7.3, which is sampling distributions with means, and so hopefully this will be clear for you. But first of all, I just want to bring up a context and really explain the concepts of this section in the context here. So the context is, it is thought that the times that it takes workers at a clock factory to assemble clocks, the times have a mean of 22.4 and a standard deviation of 3.2. The manager of the factory takes an SRS of 40, so there's our sample size, of the workers, and find that they assemble clocks with a mean of 23.1. Assume that the true mean is actually 22.4, like it says up there. And so this 23.1, that is a sample statistic. That is a sample mean. It is the mean of those 40 workers, not of all of the workers. Now, we don't know how many workers there are at this factory. We really have to assume there's more than 400 because our population size has to be at least 10 times our sample size. But our population here in this situation is all of the workers in this factory. And the parameter is the mean amount of time it takes them to assemble a clock, which is 22.4. So that is our mu. That is our population mean. And there's our sigma, our population standard deviation. So we're asked to describe the sampling distribution. So I want to go back and I want to explain again what a sampling distribution is and the main concepts of this chapter. So in this particular situation, we've got that the average time that it takes workers at this factory to make a clock is 22.4. And so what's happening here is this. First of all, we have what is known as our population distribution. So our population here is all of the workers at this factory. And the population distribution is all of their numbers. And in essence, the numbers here is the amount of time it takes them to make a clock. And so one worker, you may take, like 23.5, another 20.2, and so forth. So all of these X values represents a worker's time. And there's going to be hundreds of these X values in the population distribution. Hundreds. This is every worker in the whole factory. It's a large factory. And we don't know, it doesn't tell us how these X's varies. It doesn't say that it varies approximately normally, or if it's skewed right, or if it's skewed left, or if it's bimodal, or if it's uniform. We just know there's a bunch of X's, and they average, the mu, they average is 22.4. All right, so it doesn't tell us the population shape like it did earlier in the year. But believe it or not, that's really not that important when you have a sample of size 40. Now, so what is happening here is we took a sample of size 40 of these X's and averaged them. And so we got an average of those 40. An X bar, when I put a bar over the X, it means it's the average of a number of them, not just an individual X. And so our X bar here is 23.1. And that is an estimate of that 22.4, which later in the year we're not going to know that, and we're just going to estimate it, but we're going to pretend like we know it in this chapter so that we can create our theory. So, and whenever we get a sample value like this, we always say to ourselves, well, this is going to vary from mu just because of random chance, just because of sampling variability. And if I were to take another sample of size 40 and get another X bar, it's going to be different from that. And so, in that concept is creating what is known as a sampling distribution. So this is going to be our sampling distribution. Sampling distribution. Okay? It is going to be every value that X bar could possibly take. So our mean is equal to, our mu is 22.4. That is the mean of our population. And so our first X bar was like 23.1. Let's say that's right there. But if we took another sample of size 40, we get another X bar. And if we took a third sample, we get another one. If we kept going, and we kept taking samples of size 40 and finding the mean of those 40 numbers, we did that a large number of times, we would be creating what is known as a sampling distribution. It is, in essence, every value that X bar could possibly take in repeated sampling. Every value a sample statistic. And so whenever we get a sample statistic, whether it be an X bar or in the previous section a p hat, or if it's a standard deviation or an IQR or whatever it is, we always say to ourselves, wait a second, I got a sample value, but this is just one of many that I could possibly get. The true population value is almost certainly going to be different from this just because of sampling variability. So this is one of many I could have gotten, and so here's what they look like. Here's the family of all of them, and I'll be able to make calculations with them. So that is that. And don't get the sampling distribution mixed up with the sample distribution. The sample distribution would just be those 40 numbers of those 40 workers. It'd be those 40 X values if we plotted them. The sampling distribution is when you graph the X bars or the P hats. All right, so it is average data in essence. And so that's the concept of a sampling distribution. And so in this case, it asks us to describe the sampling distribution. Well, let me kind of draw that again right quick. So the sampling distribution is going to be centered at mu. It's always going to be centered at mu, which is 22.4. Okay, it's going to be centered there. Okay, and so we would say, okay, and whenever you're asked to describe a distribution, you'd first of all describe its center. You'd say, well, its center is described by the mean. We could also do the median, but in this chapter, we're just going to do the mean. So the center, we have a mean, and the mean of these X bars, or the mean of the sampling distribution, is equal to mu, and that in this case is going to equal to 22.4 minutes. Make sure and put the units as well. And then we'll come back to unusual values, but in regards to the spread, well, the main numbers we have describe the spread or the standard deviation, the IQR, and the range, but we'll go with the standard deviation. So our standard deviation is going to be this, and this is on our formula sheet. Okay, these are the 4 formulas on your formula sheet, the bottom of page 2, that relate to this chapter. These 2 are in section 7.2, and these 2 are in section 7.3. So you'll notice if it says that we have a mean mu and a standard deviation sigma, the mean of every possible value of X bar is equal to mu. So that's what we just talked about in regards to the center. The standard deviation of the X bars is going to be sigma, the population standard deviation, divided by the square root of n. And we could talk about proving that, but we don't have to really worry about that in the AP Stats curriculum. You just have to know this formula, and you have to know that it's on the formula sheet. And the other main thing you have to know about our standard deviations is that these formulas only work if our population size is at least 10 times our sample size. So keep that in mind. That's a popular question. But so anyway, our standard deviation of our X bars is equal to sigma over the square root of n. And so in that case, so that's our that's going to be 3.2 over the square root of 40. So it's 3.2 over to the square root of 40. And so let's see what that's equal to. So 3.2 divided by the square root of 40. And you could actually just leave it like that, and that'd be fine. It's approximately equal to 0.50596. So that takes care of the spread. Now let's talk about the shape of these X bars. And this is where what is known as the central limit theorem comes in. And this is sort of an incredible truth here. The shape of the sampling distribution will be approximately normal if one of 2 things is true. Approximately normal if the population varies approximately normally, and we don't know that here. It doesn't say up here that the times vary approximately normally, or to assume normality, or anything like that. And so these X bars and these X's, so the population, once again, it didn't tell us anything about these X values, about how they vary, except that they average 22.4. So it could be right skewed, could be left skewed, it could be normal, or it could be uniform. We don't know. So we don't know that. But here's sort of an amazing thing. The sampling distribution, these X bars will be approximately normal if the population varies approximately normal, or if our sample size is large, if n is greater than or equal to 30. And that's our rule of thumb. That number is much debated in the world of stats. In some books you'll see like 25, in some books you'll see 50, but we've sort of settled on a rough estimate of 30. It depends on how skewed the population is, and we don't know that, but in general, if it's 30, then we'd say it's approximately normal. So in this case, we would say the shape is approximately normal because our n, in fact, is equal to 40. So all of these X bars are an average of 40 values. And so what that average of 40, it's going to average out unusual values. And it's going to sort of, in a way, average out the skewness, so to speak. And it will create kind of relatively small variability and bunch these together in a mound-shaped, symmetrical, approximately normal distribution. So to describe the distribution, you would say, well, the center is described by the mean of that, the spread is described by the standard deviation of that, the shape is approximately normal because of the large sample size. And by saying the shape is approximately normal, that takes care of the unusual values or the outliers as well. Anyway, so what is the central limit theorem, which is one of the key concepts in the world of AP Stats, and it's really sort of an incredible concept that we're going to talk about, and it is this. If your sample size is large, in other words, if n is large, and like I said, our rule of thumb is going to be, let's say, greater than 30. Our rule of thumb, then the sampling distribution of x bar, in other words, every value x bar could possibly take, will be approximately normal. And it doesn't matter if your population is skewed. It's sort of an amazing thing. We're going to be able to take like distributions that are really skewed. For instance, like let's say a salary distribution for a company, which a lot of times is heavily right skewed. We're going to be able to make it approximately normal. Or if there's a distribution that's left skewed, or if there's a distribution that's uniform, or if there's a distribution that's bimodal, it doesn't matter. As long as our sample size is large, the sampling distribution will be approximately normal, and we'll be able to do normal calculations with, like we're going to do down here. In other words, use normal CDF or our normal tables. And so that is, in essence, the central limit theorem, and that the mean of these x bars will, in fact, equal mu, and the standard deviation of these x bars will equal sigma over the square root of n. And those two things are on your formula sheet. And of course, now this formula works once again if our population size is at least 10 times our sample size. So, and in this case, there has to be at least 400 workers in the factory. Otherwise, this formula breaks down. But if there's less than 400 workers in the factory, it may be easiest just take a census anyway and just see, and actually find what mu is exactly equal to. So why is the sampling distribution approximate? Because of what I just said. Because n is equal to 40, which is greater than 30. So it's approximately, the sampling distribution is approximately normal by the central limit theorem, which you can just abbreviate it as CLT. What fact allows you to use the formula for the standard deviation? I've already said it twice, is that the population size, big N, is greater than or equal to 10 times little n, and so you would say there must be at least 400 workers at the factory for our population size be at least 10 times our sample size. Otherwise, you're significantly changing the population by the fact that you're not using replacement. Okay, and so here we go. If it really does, if the average really is 22.4 for these people to assemble a clock, what is the probability you get a sample mean of 23.1 or more in a sample of size 40? Well, we'll go back to our sampling distribution. So our sampling distribution is looking like this once again. It's going to be approximately normal, so it's going to be a label that is normal. Every time you draw a distribution, a normal labeled as normal, its mean is going to be 22.4, and sigma, as we've said, is 0.50596. So going up one standard deviation, so adding that right quick, so that's going to be 22.906 approximately, 22.9, that'd be one standard deviation above it. And so you could subtract that to find one standard deviation below it. What the heck, I'll do that. 22.4 minus 0.50596 or something like that. And so that's about 21.89. So that's one standard deviation below it. So we're at 23.1. So if you were to, in essence, randomly pick one of these values of x bar, what's the probability that it'd be greater than 23.1? So this would be 23.1 up here somewhere. All right, and so what's the probability of that or more? So we need to find the area of this normal curve that is above 23.1. And once again, it doesn't say normal here anywhere in this up here. It doesn't say normal. Why can we use normal CDF, and why can we use a normal curve? Because of the central limit theorem, because of what we just said. So we would say normal CDF, and then that would be 23.1 to infinity. Our mean is 22.4, and our standard deviation is about 0.50596, and properly label these: lower bound, upper bound, the mu of our x bars, the sigma of our x bars, like that. And by the way, don't get this notation wrong, or you can get docked a point. So if you can't remember this notation, it's on your formula sheet, but if you can't remember it, just write the word mean, write the word standard deviation. And so let's do that with our little calculator. And so we will say second distribution, go down to normal CDF. So normal CDF, so we say 23.1 to infinity. If you forget infinity, just put like 9 million or whatever, and that's fine. And then our mean is 22.4, and our standard deviation, and I like having the somewhat exact number. It's going to be 3.2 divided by the square root of 40. I do believe that's right. Yes. So there you go. Now, many calculators will just immediately take you to this screen. They won't have that last screen we just had where you could enter in each of the little parameters, but just take you to right here, and you have to enter those numbers like that. But anyway, so the number we get is 0.083256. And so this number is in essence what we're going to call a p-value. It is assuming that it takes workers 22.4 minutes on average to assemble. The probability that you're going to take a sample of 40 of them and get an average of 23.1, it's about an 8% chance. In other words, it's not that unusual. Okay, if it was below 5%, we would go, whoa, something is unusual here. It's taking these workers, a lot longer to assemble the clocks than I expect. And so this gives us, sort of an expectation, or, if we're testing this figure, someone says, well, it takes our workers on average 22.4 minutes to assemble a clock. Well, okay, so we decide we're going to test that claim, and we take a sample of 40 of them, and they average 23.1, which is more than that. Okay? And so we say to ourselves, and so someone may say, well, that could be just sampling variability. You're not expecting these 40 to average just exactly the population average. There's going to be sampling variability. Well, and so what we are finding here is the conditional probability. The probability, one thing given another. Given it takes all the workers 22.4 minutes to assemble the clock, the probability that the average of 40 randomly selected ones to be 23.1, the probability that that is going to happen is it's over 8%. So in other words, it's not statistically significant. It's not that unusual. It happens a decent amount of the time. So there's no reason to doubt the 22.4 claim. The fact that our sample value was greater than that, it's plausible just due to sampling variability. But if this was like 0.04 or something, below 0.05, we would say, hey, that is a statistically significant result. We have reason to doubt this 22.4 claim, assuming that we didn't get any sort of biased data. But we did get a random sample. It said an SRS, and so that should take care of bias in that regard, as long as we measured them fairly. So, okay, how long would you have to, or how large would you have to make your sample size if you wanted the standard deviation of the sampling distribution to be at most 0.25? Well, so formula for the standard deviation of the sampling distribution. Gee, I forgot what that was. Well, there it is, right on your formula sheet. The standard deviation of your x bars of your sampling distribution is sigma over the square root of n. So we'll use this formula. The standard deviation of your x bars is equal to sigma over the square root of n. This type of problem is a very popular problem, is how big does your sample size need to be? It's something, anytime you do any sort of surveying or anything like that, one of the questions you have to ask is how big does our sample need to be? And the answer to that very typically is, well, how big does we want our standard deviation to be? Or when we do confidence intervals later in the year, how big does our margin of error need to be? And so in this case, we want our standard deviation or our sampling distribution to be at most 0.25. So we want this thing to be less than or equal to that. And well, it tells us up here that sigma is 3.2. And so we'll divide that by the square root of n. And then we'll just use our algebra skills to solve this for n. So to solve this for n, I've got to get it out of the denominator. So I'll multiply both sides by the square root of n like that. And so I've got the square root of n times 0.25. It's got to be greater than or equal to 3.2 like that. And then I'll just divide both sides by 0.25. Divide by 0.25. And so I get that the square root of n is greater than or equal to, let's see what this is, 3.2 divided by 0.25. And so that is equal to 12.8. Then I square both sides here, and so when I square both sides, I would get 12.8 squared, and that gives me 163.84. So my sample size needs to be greater than or equal to that. Now my sample size has to be an integer, and so you always round up. Even if this had been like below 0.5, even if this had been 163.14, you would say our sample size needs to be 164 workers. Okay, and so that so that will ensure, by the way, by rounding up, it ensures that our standard deviation will actually, in this case, be a little bit below 0.25. So that's how you do that problem. And then, okay, let's look at this situation. All right, so our next context is this. All right, the salmon in Nicole's ponds have weights that follow a very skewed distribution. Aha. So we don't have normality. We just know it's very skewed. And by the way, it doesn't say skewed right or skewed left. It just says very skewed, with a mean of 8.4 and a standard deviation of 2.7. So that is the weights of all of her salmon, by the way. So this is looking like a mean that's a mu. It doesn't say that she took a sample of them and found a mean. And so in which case that would be an X bar. That would be a mean of a sample. And this could be the standard deviation of a sample, which is going to be more of an issue in a couple of chapters, by the way. But and so this is our sigma. That is our population standard deviation, the average amount that these things vary from the mean. If you were to randomly select one of Nicole's salmon, what's the probability it weighs more than 8 pounds? Well, we can't answer this question because it doesn't say that it varies normally or uniformly or any way. So we can't answer this because we don't know how the distribution varies. We don't have a sampling distribution here. It didn't say we took a sample of size 30 or something like that, which would ensure normality. It just says we're taking one of them. So we don't know how the population is varying, so we don't have normality. All right, but in this next one, it says you randomly select 30 of them. Randomly select. Now, the fact that they've randomly selected means we have eliminated bias in selection in that regard. But we've randomly selected them. Now, you may make the case, well, it'd be really difficult to randomly select fish because we'd have to number all of them and go through that whole process. But we're just assuming that Nicole did that because it says it here. If you've randomly selected 30 of them, so now what we've got is we've created a sampling distribution. And the mean of this sampling distribution will be 8.4, right there, and it will be approximately normal. It'll be approximately normal because of the central limit theorem. And so every point on here represents a potential X bar, a potential sample of an average of 30 of them. So what's the probability this is going to be more than 9? So I'll just say, I know 9's more than 8.4. I don't know where it is up here, but this is just for reference. It says more, with probably the mean way to be, in other words, probably the mean weight. Mean is an X bar of the sample. So the mean would be more than 9. And so we'd say, well, we can use normal CDF. And so that'd be more than 9. So that's 9 to infinity. Our mean is 8.4. And our standard deviation of our sampling distribution is going to be sigma 2.7 divided by the square root of our sample size, just like that. So that's lower bound, That's upper bound. That is the mean of our x bars. That is the sigma of our x bars, right, like that. And so that, let's see what that is equal to. That is equal to, well, I'll go ahead and do it on my calculator. What the heck? So we would go second distribution, right there above the vars button, and go normal CDF. And so we are going from 9 to infinity, or just a big number. And so we are going to 8.4 standard deviation, 2.7 divided by the square root of 40. And like I said, I like to enter that somewhat exact number just like that in there, just to be more exact. And so we go like that. And so that is equal to 0.07994 approximately. So in other words, it's not that unusual. Even though the average is 8.4, 9 is more than that, but it's not statistically significantly more for you to select 30 of them and average 9. There's no reason to doubt this 8.4 figure. There's no reason to say to Nicole, hey, Nicole, you're claiming your fish have an average at 8.4. I just got 30 of them and averaged their weight, and it's 9, and that's more than 8.4. Yes, it is, but this is telling us it's not statistically significantly more than 8.4. If this was below 0.05 in general, we would say, hey, we have statistically significant evidence that the mean weight of these fish is actually, that mu is actually more than 8.4. But anyway, and so in this problem right here, almost this exact problem occurred in the exam a few years ago, and that is this. Which of these is more likely? Taking a sample of size 40 of Nicole's salmon and getting a mean weight of greater than 9, or taking a sample of size 80 and getting a mean weight of greater than 9. Well, let's think about this. And the in general principle here is that the bigger your sample size is, the less variability you're going to have. And so the less likely you're going to have unusual values or values different from the mean. Now, we can find these exact values in this case. So if the sample size is 40, the probability that it's going to be normal CDF, certainly the central limit theorem applies here because of the sample size is 40. Normal CDF from 9 to infinity, our mean is 8.4. Our standard deviation is 2.7 divided by the square root of our sample size. And when we do that, we get 0.07994. And actually, that's not right. I'm sorry. Let me go back. I made a mistake up here. I apologize for this. Wait, no. Let me see. I think I might have made a mistake. Yeah, I entered the wrong number here. This should be, maybe you noticed that. I apologize for that. This should be 30. There, and so I got ahead of myself. So this, in fact, is 0.11177, and so this should, I accidentally entered 40 there instead of 30 in my calculator. So, so that's that. But yeah, when you enter 40 here, when your sample size is 40, it becomes this. So by the way, what you'll notice, this probability goes down, and so what's taking a sample of size 80? Well, everything else is the same except for our sample size. So this would be 8.4, and so this would be 2.7 divided by the square root of 80. And when you do that, you would get, and matter of fact, you can quickly change that by if you just hit second entry, it'll enter the last command on your calculator, which the entry button is right above the enter button right there. If you do second entry, I can just change this to 80. And so I can do that quickly. So this would be 0.023427. Okay? And so therefore, so in what these numbers tell us, this is the probability that assuming that 8.4 is right, the probability that we would get a mean of 9 or more is about an 8% chance. But the probability, if we take a sample of size 80, the probability that the mean of those 80 values is going to be bigger than 9, it's only about a 2% chance. So with the bigger sample size, it's less likely to get values away from the mean. And so in this case, we would which one is more likely? Well, A is more likely. A is more likely. Now, when it asked this on the exam before, it actually didn't give you the standard deviation, and so you just had to understand the concept of whenever you have a bigger sample size, values away from the mean are less likely because there's less variability in your sampling distribution. And so that's sort of what you had to say there. You'd say, well, a sample size 49 is more likely to occur because it's away from the mean, and values away from the mean are more likely with the smaller sample size. With the bigger sample size, so if you have, let's say, n is equal to 40, our sampling distribution will be approximately normal, like that, okay, let's say. But so it'll vary around the mean. But if n is equal to 80, there's going to be less variability. It's going to be higher like that and lower on the tails. There's going to be more values closer to the mean. So a value away from the mean is less likely with the bigger sample size. Okay, thanks for watching the video. Sorry about that mistake that I made up here, but I corrected it. So anyway, but thanks again for watching.